When light enters a tiny opening, it bends and makes a special image on the screen. What causes this strange behavior of light? Imagine a group of balls moving at the same speed towards an obstacle with an opening. The balls that pass through the opening continue to move in a straight line. These balls fall precisely opposite the opening. The outcome is not unexpected, as balls are physical objects. Every object maintains its straight-line motion unless acted upon by an external force, the law of inertia. If we illuminate an obstacle, something different occurs. Some rays seem to bend to the side. This part is easy to explain. Light rays pass through broad opening at various angles, illuminating areas not directly across from the opening. This is known as partial shadow. How do light rays illuminate regions beyond the direct light path? The closest points where the waves have the same phase make up the wavefront. The wavefront appears flat when the wave source is far away. Huygens' principle, which dates back to the 17th century, states that every point a wave affects is a new wave source. A new flat wavefront is created by the combination of these waves. It appears that the wavefront has shifted to a new position. What happens when a flat wavefront hits an obstacle with an opening? A new flat wavefront appears ahead. However, beyond the obstruction, waves travel varying distances to the same destination. This causes a phase difference between the interfering waves, resulting in a less defined, curved wavefront. Still, light can get into these hidden places. It bends around the obstacle. This is diffraction, and it's not limited to light. It occurs in all types of waves. A particular instance of diffraction happens when light interacts with an opening of the size comparable to the wavelength of light. When light is directed from the left, a distinct interference pattern appears on the right, alternating bright and dark regions. What caused this phenomenon? Let's focus on a small opening where the distance from the opening to the screen is significantly greater than the size of the opening itself. In this scenario, we can assume that all rays emanating from the opening and reaching the screen are parallel. Light rays that are perpendicular to the barrier pass without changing their path. Constructive interference between these rays creates a central peak on the screen. Light rays that change directions act differently. Let's consider the rays that bend at the angle theta such that the optical path difference between the first and the last ray equals the wavelength of the light used, lambda. The angle between the normal to the rays that change direction and the barrier is also theta, as these angles have mutually perpendicular sides. By examining the resulting right triangle, we can state that sine theta equals lambda over A, opposite side over hypotenuse. Consequently, the optical path difference between the bottommost ray and the ray in the middle is precisely lambda half. These rays are in opposite phase and cancel each other out. For each ray in the lower half of the light beam, there is a ray in the upper half of the light beam in opposite phase. All rays in the lower half of the beam are cancelled out by rays in the upper half. As a result, there will be a dark spot on the screen, minima caused by destructive interference. Everything occurring on the upper side of the opening is mirrored on the lower side. If the path difference between the first and the last ray is 3 lambda halves, the sine of the angle theta will be expressed as 3 lambda over 2a. Following the same reasoning as before, for every ray in the lower third of the light beam, there is a ray in the middle third of the light beam in the opposite phase. All rays in the second and third segment of the light beam cancel each other out. The rays from the first segment are not cancelled out. They reach the screen and create secondary maxima on both sides of the central maximum. These maxima are less luminous than the central one due to partial destructive interference. This explains the unique diffraction pattern observed on a distant screen. The formula used to calculate the positions of the minima is A times sine theta equals plus minus n times lambda, where n is an integer. A diffraction pattern can also be obtained when light passes through two closely spaced small openings, or through a series of openings known as diffraction grating. But the principle remains the same.